so just kind of something which everyone knows, so you should probably also know. So so remember that when we talked about the norm of a matrix, so we have a matrix A, norm of a matrix A. So it was equal to the maximum of the change in the length. Right? So you looked at the vector x, look at the image of this vector under the transformation A. It's so form the ratio of the lengths. So this is length of vector Ax, this is length of vector x, and maximizes over all possible choices of vectors, but assume that x not zero vector. So right, so this was a definition, and well, kind of you could also write it with a square of a square is equal to the maximum of Ax. And so now you can just write it in using the scalar product, the dot product of this thing, and form this ratio, and also can write it as a, right, so you can write it as a maximum of x A star A x, so you can take A and put it on the other side of the scalar product. It's kind of, yeah. And so kind of this is a maximum, this maximum x not equal to 0. And so this is true for every matrix, so kind of whether it's square or not square matrix, so this is just a definition of a norm essentially, right? So and after that we somehow relate it to the largest singular value, so you can relate it to the largest singular value. But so if matrix, if A is symmetric square matrix, then you can also write that A is equal to U lambda U star, right? So this is a kind of, so where U is orthogonal, lambda is diagonal with the eigenvalues on the main diagonal. And so you can write like this, and also after that you can say that, so we proved that actually the norm of A is equal to the norm of lambda. So somehow using this thing, so the norm, so kind of the norm of is not changing if you apply unitary transformations on this thing. Right? So and so essentially kind of you can plug it in here, I think, so kind of, and you'll get that the norm is equal to this thing, so square of the norm. So and so and for lambda, right, so for lambda you can write it down this form, right? So for lambda you can just write down what it is. Right? So if you kind of calculate the norm of the lambda, so calculate the norm of the lambda square, so it will be just equal to the maximum, and x not equal to 0, and after that he'll be something like lambda 1 x1 squared plus lambda n x n squared right, and sorry, kind of. So his will be kind of so. So if you do kind of, so if you want, so do this maximization, so this is we know, right? So if you want to do this maximization and plug it lambda here, right, then will be similar lambda squared here. So here should be lambda squared, lambda n squared, and here is x1 squared. So x1 squared plus 1 plus xn squared. So this is kind of also preliminary, all this stuff preliminary, but kind of, so if you do this maximization, kind of you just maximize this function, you can also do the maximization, kind of, so maximize this thing, subject that this is equal to the constant. After that, you just use something like a kind of Lagrange multipliers method and you just do the maximization, and of course you will find that the maximum of this thing, so this is actually equal to lambda 1 over square if you kind of assume that lambda 1 greater than equal than lambda 2, so squared greater than equal than so on. So just this will be maximum square of an eigenvalue. Okay, so you look all eigenvalues, take the square of them, choose the maximum one of them. So this will be kind of this form will be maximized by this lambda 1 squared. So what I'm just saying, you can calculate it and find this. Okay, so the upshot kind of all this stuff that the lambda 1 squared is the maximum of this form. So it's the maximum of x. Well, a star ax, in this case, it's just a squared x, right, divided by x, and x not equal to 0. So just kind of, so it just kind of, I didn't want to kind of, this is nothing, it just kind of, just shows kind of, this whole argument shows that if you have a symmetric matrix, then for the symmetric matrix, the norm is equal to the absolute value of the largest eigenvalue, largest absolute value of eigenvalue. So this is a square of the norm, right? So because this is kind of, this is a square of the norm. So, okay, so the norm itself is equal to the largest absolute value of eigenvalue. Right? And it's this largest absolute value of eigenvalue is equal to the maximum of this form. Nothing more than. And so now, so the Rayleigh quotient is just a very small modification of this idea. So instead of looking on the maximum of this form, which will give you the square of the eigenvalue, you just look at the another form without this square. And so this will be called a Rayleigh quotient, and the maximum of this form give you the maximum eigenvalue. So that's the idea. So very small kind of ideological change, but kind of just kind of what it gives you. So so definition. So if A is a symmetric matrix, and symmetric matrix. So in general, Hermitian, I think, matrix. So here's looking at a real case. This is symmetric matrix, then R of, say, X, and by definition just equal to X, AX divided by XX. So this is a scalar product of X and AX. This is scalar, so it's just square of the length. So it's called the Rayleigh, quotient or ratio quotient of A. So kind of a theorem, so which is suggested by this kind of result. So the theorem just says that lambda 1. Okay, so suppose so lambda 1 greater than lambda 2 greater, so greater or equal than lambda n. So our eigenvalues of okay, symmetric matrix A, then so then so lambda 1 is equal to the maximum of this Rx, so maximum of this quotient, so kind of you can write it x ax divided by x ax, so then x not equal to 0, right? And so lambda n, so the smallest eigenvalue is equal to minimum of Rx, x not equal to 0. Yeah, so this is called sometimes Rayleigh and Ritz theorem. So, and both are British physicists, and actually they studied not the matrices, but they studied a kind of some kind of a operators in physics. Right? So, kind of this is a simplification of the result in some sense. It's the same meaning, but it's kind of they looked at something like operators, something like so it's a so integral operators, and so there was a corresponding meaning of eigenvalues. So kind of there is a corresponding. So here's x divided by x. Sorry. So corresponding scalar product of functions, not vectors, but functions. So operators operate on the functions, not on the vectors, but kind of everything is very similar kind of to this. And so we proved this theorem. And just kind of it allowed you how to find out these eigenvalues. And eigenvalues actually had a meaning in this their problem. It was something like there was a kind of like a membrane which was vibrating, and this lambda 1, lambda n were something like a frequencies of the vibrations, possible frequencies of the vibrations. And so kind of they were interested in finding these frequencies, and so this is one. So frequency, this is kind of the main frequency of this vibration. So they kind of found a way, kind of, so they found this theorem when studying this problem, this physical problem. And so now the proof, well, I'm not sure kind of if it's, so this is more like will be a lecture without many proofs, but in this case, it's kind of very easy proof. So in this case, what you need to do is, right, so, so we'll need to show, you look at this, so what it says essentially. This thing says that that x ax is bounded on the one side by lambda 1, so lambda 1 is the largest, lambda 1 xx, and on the other side it's bounded by lambda n xx. So the ratio xax to xx, it's between lambda 1 and lambda n. So it cannot be larger, cannot be larger, the ratio cannot be larger than lambda 1, cannot be smaller than lambda n. And the second thing, it says that it is achieved. Right? So it's achieved, this maximum is achieved at some vector. Right? So there is an equality for some choice of x, there is an equality in these inequalities. And so you need to show two things, that first of all, this is true, so this is true. And second thing, that there is a choice of x such that this equality is achieved. And now, so why this is true thing? So kind of again, so we can write that A is equal to U lambda U star. So this is a kind of, this is a decomposition. This is a eigenvalue decomposition or spectral. It's also called, I forgot to tell you, spectral decomposition, right? So it's called spectral decomposition of the symmetric matrix A. And so, so we can plug it in here and see that AX is equal to okay, so X U lambda U star X. So then take U, one of the U's on the other side, it will be U star X lambda U star X, right, which is the same as, say, call it this U star X as Y. So this is Y lambda Y, right? So where Y is equal to this U star X. Yeah, so now this Y lambda Y, you can write it down. So you can write that this Y lambda Y, just kind of, it's Y star lambda Y. So you just kind of write it down and calculate, and this is just Y. So it's just lambda 1 Y1, so square plus lambda 2 Y2 square plus so on plus lambda n Y squared. So lambda n yn squared. And so this is just a vector with the components. Yeah, so this y is, so this y1, y2, yn is the components of this vector y. So this is just basically saying y1, yn multiplied by this lambda 1, lambda n. So, sorry, here's the row vector. So here's y1, so yn. So you multiply it. So here's 0, 0. So you multiply it, get this form. And then after that, you look at this thing, and well, it's obvious that lambda 1 is the largest, lambda n is the smallest. All these numbers are positive numbers. So kind of it's clearly smaller than lambda 1 multiplied by y1 squared plus so on plus yn squared. Because, well, kind of all these numbers, lambda 2, lambda n, they are smaller. So kind of if you increase these numbers, so if you add lambda 1 minus lambda 2 here, then this thing becomes larger because this is a positive thing. So kind of, so it's clearly true. So greater than equal than lambda n y1 squared plus yn squared. And so it's almost like we had here, right? So but here, so this is lambda 1 y, right? And this is lambda n y. So it's almost like here, but here we have a XX, and here's YY. So this is the length of vector X, squared length of vector X, but we know kind of so this is so Y is equal to Y star multiplied by X, and Y is a unitary transformation. So unitary transformation doesn't change lengths. And so you can know that Y is equal to XX. And so if you plug in this in here, then you'll get this inequalities. So this is just kind of very easy argument. So it says, okay, so this is a true kind of inequalities. We are satisfied. So why kind of the minimum achieved? Well, just take eigenvectors corresponding to these eigenvalues. So and just calculate, then it gives, if you take eigenvector which corresponds to eigenvalue lambda 1, so then you'll have A multiplied by X will be lambda 1X. You take lambda 1 outside and you'll get an equality here. So these inequalities are achieved on the corresponding eigenvectors. So inequalities just become equalities at eigenvectors corresponding to lambda 1 and lambda n. So okay, so this is just kind of the theorem. And so now it can be extended. So suppose we are interested not in the smallest or largest. Suppose you are interested in the second largest or kind of third largest, something like an intermediate inequality. Okay, so in this case, so extension. So now you are okay. So you assume. So one thing is to assume that you found some of this inequality, some of the eigenvalues, and so there are two extensions. Actually, I'm talking just about one. So suppose you already know that you found. Well, not found, but just suppose that you know what's lambda 1 and lambda k minus 1, and you know the corresponding eigenvectors. So let v k minus 1, it will be span of u1 uk minus 1 such that where u kind of I is the eigenvector corresponding to lambda maybe I should say also they all are orthogonal. So in principle, there is a possibility that there is a possibility of equality, right? So lambda 1 is equal to lambda 2. In this case, so we assumed that you choose the eigenvectors perpendicular to each other. And so theoretically, if you kind of have lambda 1 equal to lambda 2, you could choose eigenvalues which are just the same vector. So kind of, well, so this is a kind of, so maybe you should kind of say that U1, UK minus 1 is the system, orthonormal system of eigenvectors corresponding to the first K minus 1 eigenvalue. So this would be more proper, probably, to say. So, but I don't want to rewrite it. So, okay, so meaning is clear, right? So just kind of VK minus 1 is a span of eigenvectors. Then, so we want to extend this thing, which says that this is a maximum or minimum here, and I'm extending this with its maximum. So then lambda k, kind of a new eigenvalue, is just maximum of this ratio Rx. Overall x, which are not zero, and also which are perpendicular to this vk minus 1. So perpendicular means that kind of, if you take scalar product of x with every vector in vk minus 1, it gives you 0. So, well, and another extension would be related to the minimum. So you could write similar extension. So now the explanation kind of this, maybe kind of not a proof, but explanation of this, that so that if you look at, so there is a kind of okay, so you can introduce a vector space which is a perpendicular and call it somehow. So kind of, so omega is, so W, maybe kind of some subscript here. So, and you can write it, this is k minus 1 perpendicular. So it's a subspace which is perpendicular to vk minus 1. And now it's actually, so you know that the symmetric matrix have all our eigenvectors which are perpendicular to each other. At least you can choose the eigenvectors such that they're perpendicular. And so, well, so you can write it maybe kind of, so if with some different, you can write it as a span of u k and un. So maybe kind of, it's again, so it's not an exact proof, it's just explanation I'm writing here. So you can write it like that one, right? And after that say, all right, so in particular, so what happens if you apply the transformation A to this subspace, to any vector in this omega? Okay, so, well, kind of then every vector in this, within this W, it's a linear combination of this UK plus 1 UN. So if you apply the matrix A, so UK just kind of will get into vector which is a proportional to UK. So UN is also gets to some vector which is a proportional. So the upshot that this linear combination of these vectors will go to the linear combination of the same vectors. And so that means that, well, if you apply A to W, then the result will be inside W. And so kind of, right? So maybe kind of, yeah. So it will be something like that. And so now it means that you can look at the restriction kind of. So the restriction of A to W, right? Okay, so you can restrict because it's kind of, if you apply A to W, it's still be inside the W. And you can look at this, well, actually the eigenvalues of this restriction will be this lambda K, lambda N. So it has eigenvalues, so lambda K, so greater than or equal lambda K plus 1, greater equal than so on, greater than equal lambda n. And so the point is that it has the same eigenvalues, but except that it doesn't have the first k minus 1. Right? And after that, you go to the Rayleigh-Ritz theorem and says that the largest of them, which is lambda k, will be equal to the maximum of the Rayleigh quotient on this subspace, on W. So, and this is exactly what we wanted to prove. So kind of it's a maximum of the Rayleigh quotient. Then you restrict that x so belongs to this W. And it's perpendicular to the k minus 1. So kind of just because kind of, well, if you look at the symmetric matrix, then the eigenvalues, they are all perpendicular. So this implies that this extension is holds. So then if you restrict to some subspace spanned by some eigenvectors and act by this matrix on this subspace, then it will go to itself. And the second thing that it's perpendicular to whatever else was before that. And so this is an extension. So it's kind of maybe kind of called a part of this Rayleigh-Ritz theorem. So I mentioned several times that this results like that holds. And so, and this is essentially kind of how the algorithms for finding the eigenvalues, some algorithms for finding eigenvalues work. So you find the largest one, restrict to the space which is perpendicular, find the largest in that, restrict to the space to be perpendicular to the two found eigenvectors, and continue until you find all there. So this is the basis for this kind of thing that I told you before. And so now after that, this is very nice. It's actually something maybe which is only this thing is needed in practice. But there is another extension which is very nice and apparently very useful in theory. And this extension is called current Fisher theorem. So another extension. So we're kind of it's benefit. Well, okay, let me formulate it and say maybe what's the benefit. So theorem. So this is a current Fisher. And also was proved when was so usually in application to the problem of mathematical physics. So also again, not about the matrices, but about the operators. And it just says this thing. So it just says that lambda k. Okay, so okay, so it's equal. Okay, so here will be a maximum of Rayleigh. Okay, so the Rayleigh ratio. Okay, so x not equal to 0, and here's x perpendicular to v, right? So similar, like very similar to this thing, but here just, so here's vk minus 1 was the span of everything, and here just say, so okay, just take the minimum of this maximum overall possible v such that the dimension of v is equal to k minus 1. Okay, so this is the condition. And so for the largest of them, so if lambda 1, when dimension of v is equal to 0, well, it means that just kind of there is no restriction. So 0 spaced vector space is just 0. So everything is perpendicular to 0, right? So if you scalar product with 0 vector, it will give you 0. So everything kind of perpendicular. And so if you look at the k equal to 2, it means take any direction, so any line, right? And take the maximum on the space which are perpendicular to this line. Take the maximum of this thing. So you'll get a bunch of the numbers which depends on the line. So take the smallest of them. Right? The smallest of them will give you the lambda 1. Right? So essentially it says that this vk minus 1 gives you a minimizer here. And so, but this is okay. I'm not going to prove it. This theorem. This is a kind of seems to be a not so easy kind of. Well, I just don't have time. Don't have time to do it. And, but okay. So and well, kind of there is a maximum part. So it's maximum over minimum. But I will not write it because I didn't write the corresponding extension here. But there is also kind of max min characterization. So, but it's just don't write it. So there is a symmetric characterization as a max min. Okay. So, right. So now and after that, well, after that, I unfortunately stopped to proving anything, but formulate some extensions. So it turns out that this Courant-Fisher theorem can be used to get interesting results and results about the eigenvalues of the sum of several matrices, of two matrices usually. Right. So so let us kind of use the notation. So notation. So lambda I of A is the eigenvalue of the eigenvalue of A. So they are arranged in decreasing order. So lambda 1 A is greater than equal to lambda 2 A. So greater than equals to lambda n of A. So we just kind of arrange them in decreasing order. And now, so the question is now kind of we know what. So some information about eigenvalue of one matrix. So this field of research is about what happens if you have two matrices and say look at some function of them. Say usually sum of the two matrices. So and so here's a theorem by Rayleigh. So theorem. So Rayleigh, which kind of can be proved using this stuff. So it's based on this Courant-Fisher theorem. So let A and B be symmetric n by n times n symmetric matrices. So then it turns out that, okay, so we are interested in lambda, say maybe not I, say maybe k of A plus B. So what we can say, we know kind of eigenvalues of A and B. So and using this theorem, it turns out that you can prove that this is okay. So more or less natural thing. So lambda that's smaller than equal to lambda k of A plus largest of B. And greater than equal than lambda of k of A plus lambda n of B. Okay, so more or less natural results. So and in particular, so if B is non-negative definite, so remember that non-negative definite means that so that x bx always greater than or equal than 0, and well, kind of you can also prove that this also means that all eigenvalues are non-negative. All eigenvalues of B are non-negative. So probably something related to all this stuff. You can easily prove it. And so then in this case you'll have at lambda k of A plus B. And so let us use this inequality. So lambda n, the smallest eigenvalue, is greater than 0. So kind of, and so we can write that this is greater than or equal lambda k of A. So if you take a matrix, add a non-negative definite matrix to it, then all eigenvalues will increase. And again, this had, well, kind of its natural, but not so easy to prove theorem. And it turns out that it has a kind of physical consequences, something like, well, if you do something with a membrane, so put some heavy thing on it or something like that, then all frequencies of the vibrations will increase. And so something like it will. So, well, this is something like a kind of interesting physical meaning, actually, not easy to prove. And so this is kind of a statement of the Weyl theorem. Right? And okay, so people went even deeper in this. Right? And they proved actually another theorem, which is again interesting. And I'm just in this moment, I'm not kind of just illustrating it, what's the field or how field went in this direction, and so what you can prove, and kind of so basically given some review of some interesting stuff. So, and after that we prove so in something which is called interlacing inequalities. And so now, and so if you look at this thing, so what it says, kind of suppose you have a something like, so this is lambda, say let us something specific example, n is equal to something like a 4. So this is lambda 4 of A. So this is another lambda 3 of A. So this is say lambda 2 of A. And so this is lambda, so maybe closer, lambda 1 of A. Right? So now what this theorem says to you that if you add B, then all these eigenvalues moved to the right, they will increase. Okay? So the interlacing theorem says, so suppose that B has rank, so B, okay, so it's a non-negative definite, and has rank 1. And so what it means is that it's actually, it means that B can be written as a product of x bar for some vector x. Okay, so it's kind of every rank 1 matrix can be written in this form, right, for some x. So it's also symmetric. We always assume that this is symmetric. So if it's not symmetric, then it will be written as x. So column vector multiplied by y, and kind of so general can be x multiplied by y star, where y is another vector. But if you also assume that it is symmetric, then x should be equal to y, so this will be x star. Okay, so now kind of it's always true. So and it will be automatically positive. This thing will be automatically positive definite. Actually, I'm wrong. In general, kind of rank 1 matrix would be something like a plus minus this thing. So it also can be minus. Right? So in general, every vector will be x star if you assume condition that it is if it is symmetric, then in this case you need to have it y star is proportional, so y is proportional to x. You can take the coefficient of the proportionality outside and you can take it back in these vectors, and it will be either x star or minus x star, and kind of these are different things. So one of them have an positive, well, it's a different thing, right? So this is a, if it's not negative definite, you can write it like that, right? So so this is what is b. B is just x star for some, right? So now what's the statement here? Right? So in this case, so then, all right, so let me try to write it. So it's lambda k of a plus b. So we know that it should be greater, by this theorem, it's greater than lambda k of a. Right now, this is rank 1, so it's one eigenvector, one eigenvalue is positive, and all others are zeros. Right? So here will be at 0, and so it's just kind of this inequality. So lambda k plus b greater than lambda k. But with interlacing inequality have another thing. It says that it's actually smaller than lambda k plus 1. So k minus 1. So this is greater, right? Lambda k minus 1 of a. Well, so in assumption is that lambda of 0 of a is equal to plus infinity. So just kind of infinity, right? So and what it means here in this picture, so it means that you have a here's a lambda 4 of a plus b, but it cannot kind of become greater than lambda 3 of a. So in principle, kind of you just kind of, if it would be not necessarily a rank 1 matrix, then it could kind of be very arbitrarily large. But here it says, well, it cannot be greater than this thing. Right? This is kind of, for me, it's surprising, kind of, probably kind of, it's a kind of surprising that you can. So this, the first one can be arbitrarily large. So this is lambda 1 plus a plus b. You can get it arbitrarily large. So you can kind of, in one direction, you can spend it, right? But here, they will be interlacing. So lambda 4 of a, and then lambda 4a plus b. After that, lambda 3 of a. After that, lambda 3 of a plus b. Right? Lambda 2 of a, lambda 2 somewhere here. So something like this one. Okay, so after that, lambda 2 of a plus b. And after that, here, something like here will be lambda 1 of a plus b. Okay, so this is a kind of all, I think it's kind of very beautiful result. Right, so my computer says that it's almost out of charge. Right, so maybe kind of, okay, so almost done. So this is a big picture. So almost done. And just to relate to something which is done. So this is also kind of old results, but we will investigate it kind of in this 20th century after Rayleigh, so in detail. So you can also get these theorems for singular values, similar theorems for singular value. So now kind of very recently, by very recently, I mean around 20 years ago, there was a research in which kind of not that I was involved, but what was interesting for me, it's kind of was a part of what I wrote a thesis on, and this part of this research was about the question. So suppose you look at these matrices A and B like before, right? But here's A and B, so are symmetric, n by n matrices, and n is large. Right? Okay, so this is okay. So n is large, but it's all right. So it's not enough to say anything much. It's also kind of you need to introduce some randomness. So and suppose U is a random unitary orthogonal matrix. And so that means that kind of we can instead of B, you can think about with a diagonal matrices. Right? So A diagonal matrix, B diagonal matrix, but we can look at A plus U, B, U star. Right? And so ask the question, so what is the lambda K of these matrices? And so now what's kind of was for me what was fascinating that it turns out that you know the distribution of A and B, then in this case it turns out that you can calculate the distribution of this thing when kind of n is large. So from the distribution of this A and B, kind of it's possible to calculate what is this lambda K, well at least the distribution of this lambda K. So I think that the most recent results actually gives you specific formulas for individual eigenvalues, but it kind of, and so kind of this is again so something which is kind of recently was done, and so this relies on a lot of this theory. All right. Okay, so that's it. So and so okay, so this is a relation, so matrix theory, so okay, so it's a random matrix theory. So this was done when the kind of the people started random matrix theory, which was a kind of was and is a popular research topic. And another thing which I was interested in, a free probability, which is a tool from completely different area of mathematics. So it's kind of the kind of a study of this eigenvalues turns out that it's related to the kind of a mix of a random matrix theory and free probability theory. So okay, so this is a good thing, a place to stop. So that's it, kind of. So